Good afternoon, and welcome to the Smithsonian National Air and Space Museum. I'm curator Dr. Jennifer Lavasser. I work in our space history department here at the museum. I'm curator for astronaut equipment and cameras. And I welcome all of you to today's program, which is on appropriate attire. I want to thank our sponsors for What's New in Aerospace, Boeing. And I hope the show is informative, and that to some degree involves all of you. So I want to make sure you have the opportunity to ask lots of questions. We'll have a couple of breaks in between talks. You'll get a chance to stand up the microphone, which is right here at the center. We also have an online audience at home, and so they'll have the opportunity to ask questions as well. So welcome to all of you at home as well. So let's get started. Our program is on appropriate attire of the past, present, and future of astronauts. What is it that they need to be in space, to do spacewalks, and to do other work in space? Leaving the spacecraft means that you need to have essentially a personal spacecraft around you. You've got to carry everything with you as you leave the vehicle. Ed White was the first American to do a spacewalk back in 1965 on his Gemini 4 mission. And he had an umbilical tying him back to the spacecraft. And I think we have an image of that, just to set the context a little bit. We also had a spacewalking exhibition here last year, which certainly set the stage as far as artifacts go, and we displayed a number of pieces you see in that photograph. The Apollo 11 astronauts were the first astronauts to walk on the surface of the moon, carrying their life support in backpacks, which were left on the moon. And astronauts who work on the space shuttle and space station today still require a suit that protects them during those long spacewalks, sometimes around 8 hours long, to service satellites, observatories, and of course build and maintain the International Space Station. So our guests today are going to discuss the past, present, and where engineering and design of spacesuits and protecting humans is going in the future as we move beyond Earth and towards Mars. So let me make some introductions of our guests today. On my far left is Dr. Kathy Lewis. Kathy is our curator here for international programs and spacesuits. She is a specialist in Soviet and Russian programs in particular, and she's working on a comparative history of American and Russian spacesuits right now. She has her bachelor's and master's degrees in history from Yale University and a PhD in history from George Washington University. And she's also the curator for our space race exhibition right next door. And on my immediate left is Dr. Dava Newman, who is the deputy administrator at NASA. Dr. Newman has her PhD from, and master's degree actually, from MIT, where she was also a professor there for about 25 years, if I understand right. She was confirmed by the Senate last year and began her service at NASA in May of 2015. And her expertise is in the area of aerospace biomedical engineering. So join me in welcoming our guests today. And I will let Kathy get started with her presentation.
Okay. If I can get my first slide, which is actually my -1 slide. This is a collage of the spacesuits that we have in the Air and Space Museum collection. Some of them are recognizable to you, others are not. And I frequently get the question, why do you need so many spacesuits in the collection? And why do you have different types? And in fact, we have a collection of about 287 at last count. Sometimes they multiply in captivity, of spacesuits and major spacesuit parts in the collection. We have Mercury, Gemini, and Apollo that you're all familiar with, especially the 12 spacesuits that walked on the surface of the moon. And we have each of them in the national collection. But we also have suits that come from the pre-spaceflight, human spaceflight era. We have suits that are developmental suits, that are contract suits. We have suits that will never fly, that were designed for programs that never happen. But they are all important parts of the history of spacesuit development, and that's why I collect them. Not because they are defining any specific program, but they're defining the idea of a spacesuit and the concept of a spacesuit. And when I'm looking at spacesuits, I'm looking at what elements go into making them. And it's a mixture of imagination, the mission that they're assigned for, and what they're fulfilling, and engineering. When you walked into this gallery today, over ahead, and I don't know if I have it, is the Wernher von Braun Disney Ring space station. And this was designed in consultation with Wernher von Braun on his idea of what a space station would look like. It's a rotating space station that provides artificial gravity to the astronauts. This was in 1956. It was broadcast over the Walt Disney's Sunday evening program. And what we have is the space station that was used in the filming. What we do not have are the spacesuits that were designed for use in that space station. And these are photographs of those, or of drawings and a photograph of von Braun working with that spacesuit. And it's affectionately was known as the soup can suit. The astronaut would in fact do a spacewalk, climb in the spacesuit, and use these robotic arms to do construction on the space station. You could see the arranging. He would turn around in the spacesuit. And that was von Braun's concept of what the spacesuit would look like for that particular space mission working on the space station. And it's very important to remember every spacesuit has to be dedicated to the mission, to the spacecraft that they're working on. Von Braun was not the first to have inputs and insights on what a spacesuit would look like. This is a film advertisement for a Soviet film from the early 1930s, Kosmический рейс, in which the founder of the father of the Russian space program, Konstantin Tsiolkovsky, was an advisor. And this was his idea of what a spacesuit would look like for exploring the moon. And throughout, in the United States, we were watching Disney on TV, we were watching Star Trek. In Russia, in the Soviet Union, they were watching space science fiction films that also had spacesuit designs. And these were the filming models that were retained and collected at the Leningrad Scientific Film Production Association in St. Petersburg, Russia, and they were used to make a series of films on human exploration of the moon, of Mars, and of Venus. And these are some of my favorite of the suspended suits. And one thing to note that in these collections, there were not only men exploring other worlds, there were women as well. So you have different anatomies represented in developing the spacesuits. But when it came time for NASA to develop Project Mercury in 1959, they had to meet a short time frame and they had to confront reality. They had existing expertise with flight suits for pilots, and they had to merge them very quickly to get a suit that would work inside the spacecraft that they were designing to fulfill that mission. And what they had is, on your left was a Mark IV flight suit that was developed by B.F. Goodrich Company for the Navy. It was designed for fighter pilots so they could withstand rapid changes in G-forces when they were maneuvering. And there was also the MC2 suit that the David Clark Company was designing about the same time for high-altitude pilots for the Air Force. The silver color was an experiment that the David Clark Company was working with at the time to ameliorate the problems that pilots were complaining about with overheating in the cockpit. They were getting very, very hot in that very bright cockpit when they were going at very high altitudes. And the result was the Mercury spacesuit. You can see John Glenn's just outside in the Space Race Gallery next door. But the Mercury spacesuit took the Mark IV spacesuit, used the silver aluminized coating on the top for reflective purposes, just in case. They knew it was a problem for high altitude pilots, so they thought, well, we'll try it for astronauts. And it was all retrofitted to fit inside the Mercury space capsule. And that is Friendship 7. That is, unfortunately for you today, behind the barriers, but is in a case in Milestones of Flight. And for the Gemini program, NASA took a similar approach. This time they went to the David Clark Company. They took their high altitude suits, modified them, retrofitted them to the life support to the spacecraft. They didn't have to worry about, they knew that the spacesuits would work in the spacecraft, and this is Ed White, really, once again, having the time of his life, floating outside of the Gemini spacecraft. But when it came time for Apollo, they had to rethink their approach in designing spacesuits. First of all, the astronauts would have to walk. They'd been designing pilot suits up to that point, and they had to design a suit that the astronaut would have to be able to walk in order to take that first step on the surface of the moon. In addition, the astronauts would have to have a spacesuit that would operate in not one. This is the command module Columbia, as my colleagues are 3D scanning it. And they would have to work out in the Columbia, the command module, and in the lunar module. So you have a spacesuit that has to work in 3 different arenas perfectly: spacecraft, lunar module, and on the surface of the moon. And that is how the Apollo spacesuit came about. This is a fully form-fitted spacecraft. The astronaut is completely autonomous, able to walk around in space and not have to rely on any connection, any umbilicals back to the spacecraft, but also feel comfortable while in the spacecraft and operating it, and have the systems work on both sides. The astronauts needed the life support system inside the spacecraft in order to get the personal life support system working before they took a spacewalk. So they needed a perfect fit, an amazing amount of engineering. And that is Neil Armstrong's spacesuit. As it may appear in a few years here at the museum, and in 2 years, we will be putting it back on display, just to give you an idea. Now, with this combination of imagination, mission, and engineering is coming around almost full circle from the Disney wheel. And when you look at it, it was just announced a few weeks ago that Elon Musk has commissioned a Hollywood costume designer to design the spacesuit for his Dragon capsule. He's decided that he wants something daring and showing clearly the new design innovation and this really compulsion for exploring. But he's taken the design that he's gotten from the costume designer and he's re-engineering it to fit back into the spacecraft so it will work. His assumption is that with the engineering of costumes today, which are very different from 50 years ago, that he can assume that the life support will fit in because you have to have cooling and breathing supplies in costumes for Hollywood. And the designer is Jose Fernandez, who is the head of Ironworks Design and is known for designing the Iron Man costume, among others, in Hollywood movies. So, questions?
Yeah, absolutely. We're welcoming questions both online and here in the audience. If anyone in the audience wants to step up to the microphone and ask something, you're more than welcome to. And Kathy, if you want to stand or sit, feel free. But we will get things rolling.
Good afternoon. I'm Steve from Arlington, Virginia. And the question I have for the curator is, so the suits are made to survive in space. What do you have to do to have them survive in the Smithsonian in the museum?
Very good question, and I didn't plant that one. Yes, spacesuits are meant to survive in space. With temperatures of plus or minus 250 degrees Celsius. They have to survive penetration by particles traveling at 18,000 miles an hour. They have to survive the radiation. They have to be fully functional and not fail in terms of pumping oxygen into the spacesuit and pumping CO2 out of the spacesuit, all of that. But they are made of materials that are not necessarily high-tech, but more advanced synthetic materials that we use in everyday life and layered in such a way. But those materials, because they are synthetic, they are plastics. They have a half-life of 50 years. So that means John Glenn's suit, Neil Armstrong's suit, have either passed or are approaching their half-life in some of their materials. What we've discovered over the years in investigation and looking at the materials as individuals, looking at them as a whole spacesuit, is that the best environment for them is relatively low humidity at about less than 30% and at a cool but not cold temperature. That is the best way to keep the spacesuits together as a whole thing. We always get materials experts saying, well, it would be much easier for you to preserve them if you could take them all apart. Well, we can't take them all apart. They're historical objects. So we have our spacesuits stored in a storage facility at the Udvar Hazy Center, and they're in a large room that's kept under those climate conditions. What we're working on right now is finding ways to replicate those climate conditions for exhibitions so we can get more of that 287 suit collection on display for the public throughout the world, because we really would like, if we preserve them and nobody sees them, there's no point in preserving them. We want more people to be able to see the spacesuits. So finding cases that seal properly, there are amazing advances in climate systems that will maintain the climate inside a case for museum objects today. And that's what we're working on, and that is how Neil Armstrong's suit will be displayed in 2019 when it goes on display.
Hi, I'm Jared Nettles from San Jose, California, and I was wondering, maybe to both of you, what are some of the challenges that you see coming up in spacesuit design, especially as we think about going to Mars and maybe on to some of the moons, like increasingly hostile environments in space, and dealing with problems of ionizing radiation to astronauts over long periods of time. So I'm just interested in what your thoughts are in that direction.
It's a good preview question for, I think, what we're going to hear about, but go ahead.
Yeah, go ahead. You can go first, I'll go second.
Well, as I had said, the first thing you do is you have to look at the mission. The jump from Gemini to Apollo is very important because the astronauts had to walk. Now with the ISS, the astronauts don't have to walk, so the lower half of the suits are not very mobile. So everything goes to mission. As far as radiation is concerned, that is a concern, and I think Dava is probably better trained to answer that. Right.
Low weight suits, very low mass, very mobile. That's where the future we think of design and development. Radiation is maybe the number one showstopper to keep our astronauts healthy and well. Don't think it makes sense to incorporate that into the suit design. Makes sense to incorporate that into your shelters and things like that, because you need a very high dense, high massive protection of the radiation. So I kind of decouple the two, thinking about the suit and life support system design and then your habitat and rover design, which are better equipped to do the radiation protection. Thanks.
Okay, there's an online question. What lessons were learned from Apollo spacesuits that have contributed to modern spacesuits? Kathy.
First of all, no zippers. That is the first question. At the time, B.F. Goodrich had designed a really elegant sealing system, which was a compression system between two zippers. There's a rubber gasket that goes between the two zippers. When the suit is pressurized, the two zippers press together and compress the rubber gasket, and that forms a seal. And it worked perfectly well for the Apollo program. In fact, they tested and retested the suits after the missions. They were able to repressurize each of the suits without any significant increase in the loss of air inside the suits. But they are, for long-term use, they are very unreliable. They will not work, they stop working after about 5 or 6 pressurizations. And in fact, with what I've learned recently, which is amazing, they swapped out the pressure zippers on every suit right up into 2 weeks before launches on the Apollo program. So they were swapping out, and when they got to a point of failure, and putting a new zipper in. So you'll look at suits now, and because of the large part of the bulk caused by the current EMU that they use, the model of which we have outside this door, is the fact that there are large bearings, waist bearings, that have compression gaskets on the inside, but they're not zippers. That's a trade-off of weight At the time, the Apollo program had to go with the lighter weight. They were going with the full oxygen atmosphere also as a weight consideration. I'm assuming we're planning to do full atmosphere, so we're going to have to find ways to make that compression seal lighter.
Yeah, those are some design trades. We don't have to have a full atmosphere suit instead of 14.7 pounds per square inch or 1 atmosphere. It makes a lot of sense to make a suit that's, say, 3/4 of that, 10 psi, 5 psi. So there's a lot of pre-breathe reasons. So there's a lot of good reasons for mobility. You can actually reduce the pressure of the suit, and you can perform perfectly well in it. What Apollo design and suits taught me as a former research in this area is that you don't actually, on the moon in low gravity environments, 1/6 on moon, 3 you don't actually do that great bunny hop thing. That was poor biomechanics. So we get another chance at it. We'll do more of a loping, skipping across the moon like this, but not that pogo thing, because we have to put in better biomechanics and more mobility to the suit.
Another question?
Hi, my name is Evan. I'm from Boston. You may have already touched on some of the things that I was hoping to ask you about, but specifically, when we design anything, we start with small steps forward from existing technology, and there's always great leaps that happen with technological breakthroughs, similar to the aluminum coating that you've already spoken about and the compression bearings on the suits. What do you think that the next technological breakthrough, or the one beyond that may be being researched right now, what do you think that those breakthroughs are going to be for spacesuit technology?
Great question.
Some of the breakthroughs have been those small steps, and going from the existing layering of materials, what they used for Apollo, they used similar layering, but they use materials that are lighter weight and more durable. So that saves some of the weight. Going on is, as David said, lighter weight, and also gloves. Gloves are the most important part of exploration. We need our hands to explore. As humans, we use our hands to express ourselves. It's part of our brain development in using the hands. The current shuttle, ISS spacesuit, has gone through 6 generations. They're working on a 7th generation of glove. Getting a glove that both protects and is pliable and gives the astronaut a tactile sense to be able to do meaningful work, and also to be able to give quick, sharp signals to his or her companion out in space without talking, is very essential. I think it's an iterative process. They've tried a lot of things. They've gone other directions out of some experiments. Some of those 6 generations were never ever used in space, were just tested. So glove development, I think, is, at least from my perspective, and I'm writing a book on it, so is the most important and the greatest challenge in terms of spacesuit development at this point.
I hope we incorporate breakthrough technologies, and that these are, not your grandfather's suits, that they're very light, form-fitting, and I hope we can get rid of the 14 layers.
All right, we're going to move on. So Dr. Newman, take the floor.
Okay. Hi, everyone. I'm going to stand up to interact with you as well. It's my pleasure to be here. So if you're standing up, come on in, and really glad to be here. I'm going to take you to Mars and actually start a little bit beyond to tell you what we're doing, just highlight a lot of great work at NASA. So maybe, see if my clicker is working. Let's see here. Hopefully my slides are on. Let's see. There we go. The screens are a little bit dark, but hopefully you can see this at 26 years. Anyone under 26, raise your hand. All right, your entire lifetime, the Hubble Space Telescope has been searching. It's in low Earth orbit, that's not too far up, but it's searching into the solar system. We've looked back 13 billion light years, and it's still giving. So I love to show this. This is a Wonderland 2 cluster. So we're discovering every day, we get new data, new galaxies, thousands and thousands of new galaxies from Hubble. So celebrating its 26th anniversary last month. It's the gift that keeps on giving. It is the world's largest, greatest optical space telescope. Our James Webb Space Telescope, call it JWST, it will be launched in 2018. It's going to be 100 times more powerful than Hubble. So Dr. Mather says, our Nobel laureate. It's those 18 gold lenses are phenomenal. It is really going to be breakthrough in terms of dark energy and dark matter, and just helping us answer the enduring questions. Where do we come from? Maybe where are we now? Are there other habitable planets? Was there past life in the universe? These are really our enduring questions for exploration. Are we alone in the universe? And what's our past? And that informs us about our future going forward. New Horizons. Everyone paid attention to New Horizons last summer? Raise your hands. Yes, we didn't know what Pluto looked like. It was pretty fuzzy. We had never seen it. We got there in orbit last July. It's been really fun. And now we know a lot about Pluto. We keep getting images back. It's icy. A lot of interesting kind of chemical composition to it. And I count dwarf planets, as you see. Dawn, our spacecraft, I'm not sure if you've heard of our Dawn spacecraft. It's winning the most prestigious space award tonight at the Collier dinner. For Dawn is a spacecraft that right now is at another dwarf planet Ceres. This is an asteroid belt. It's in between Mars and Jupiter. And we didn't know what those two little bright eyes were shining at us, so we went closer in orbit. We still didn't know what they were. What is, what's happening? Well, we found out in December that that's a Huna Mons. So move over Mount Everest, because a Huna Mons is 5 kilometers tall and is 20 kilometers wide. So that's a mountain on dwarf planet Ceres. We're still in orbit. We're still getting data back. Where are you guys going to be July 4th? Hopefully here at the National Air and Space or at our Jet Propulsion Lab. We will be to Jupiter. So our Juno mission gets to Jupiter. We are on the countdown, and we'll get to Jupiter. It's the furthest a solar-powered spacecraft has ever flown. And we're going to open it up to citizen science, so I hope you'll all jump on our NASA website. It's called JunoCam. We're going to point at Jupiter and say, hey, world, where do you want to explore on Jupiter? And we'll put our little JunoCam and we'll explore Jupiter together. So, and we're going to have a lot of fireworks to celebrate NASA getting to Jupiter on July 4th. We have our OSIRIS-REx. This is our asteroid sample return mission. It launches this September. It's going to be the first time we ever go to an asteroid, take a sample, and it's going to take a few years for us to get it back. But again, come back and look at that characteristic, signature, looking for organics, any evidence of past life in the universe. Hopefully just late last fall, we have the evidence for flowing water on Mars. It's salty, briny, you don't want to drink it yet, but it's seasonal. This is a huge scientific breakthrough for us. We know that Mars ice caps are ice, and when you search for life in the universe, we have a saying, follow the water. Well, you can follow the ice too. We've been following the ice, but now we actually have water on Mars. And so we're looking at this. We keep taking data with our Mars Reconnaissance Orbiter, and it even gets better than water. This has a little bit of, I'm not sure if we don't need sound on this. This is a simulation of Mars has 1% carbon dioxide atmosphere, 1% of the atmosphere we have here on Earth. We know why Mars lost its atmosphere. We're still studying it, but this is very recent data of the solar radiation and the solar winds ablating the Martian, those are ions coming off the Martian surface. Now Earth, spaceship Earth, our most precious, my #1 planet, we have this really nice global magnetic field that protects us from the sun and solar radiation. Mars, not so lucky. Sister planet, half the size of Earth, but Mars not so lucky. Its atmosphere has been ablated away. Now, this is real history lesson. This is 4.5 billion years, Earth and Mars. Mars was probably wet, warm, maybe a little wild, wonderful place to be 3.5 billion years ago, and then maybe something went terribly wrong. Because today Mars is a pretty cold, I wouldn't say dead planet anymore, but we're looking at it because we're looking for the past evidence of life on Mars, and that will tell us a lot about life here on Earth and our origins and history in the solar system. So we're exploring Mars every day. I want to take you to International Space Station. This is a great auditorium because I have a really great scaled model hanging up. Space Station is as big as a football field. And we have our 6 astronauts living on board today. Anyone 16 years and younger, raise your hands. We already got the 26-year-olds. I hope there's some, there we go. Every day you've been alive, we've had our astronauts in space. Up there. It'll only take some 90 minutes to go around Earth. It's pretty fast, huh? 90 minutes. So they see a lot of beautiful sunrises and sunsets every day. Then want to make sure you know NASA is alive and well. We're actually more active in development than we've ever been in the last 4 decades. We are going from space station to back to lunar orbit, call that Earth-Moon orbit, and deep space. And how we get there is our space launch system. So I'll have a fun video for you. It's not just PowerPoints. We're building and constructing. As a matter of fact, we just put the core segment together of SLS. So here's a look at our SLS, our space launch system with Orion module on top. Exploration Mission 1, we call it EM1. In 2018, we launch our space launch system with Orion. We'll launch in the early 2020s with the Orion capsule with astronauts on board. Again, this gets us from Earth to lunar orbit first in the 2020s, and then we go onward to Mars in the 2030s. So it's really exciting. That's 1,000 companies involved, and we're working in every state in the United States for these developments of our next big, heavy lift launch. It's more powerful than Saturn V. So onward to Mars. I want to remind you a little bit, I think I'll skip this graphic, it's a little bit dark in here. We have been on Mars with our rovers and our orbiters for the past 50 years. So we celebrate our past 50 years. As I said, today we have 5 landers and orbiters at Mars today. And we have it's called our Journey to Mars. The president has charged us with landing humans, getting humans to Mars by the 2030s, and I'm up for it, and I love seeing all the folks here that I've called out. If you're under 26 or 25, because you're the Mars generation. I'm not going. I'm just trying to do everything in my power to get you there. So we will get there with boots on Mars in the coming time. I wanted to tell you a little bit about Scott Kelly's mission on Space Station, again, with this prop in the back. So again, 6 people living on International Space Station. But we had a really special opportunity in the last year. Scott Kelly was on Space Station for 1 year. It's the longest mission we've had for an International Space Station astronaut. And we studied his body and his physiology. And before, someone asked me about radiation. So on International Space Station is our first phase of Journey to Mars. We're learning how astronauts live and work in isolated, confined environments. And we did the first genetics research and science. Scott has an identical twin brother, Mark, who's down on the ground. He's the control subject, former astronaut himself. And we're able to test the 2 brothers, the 2 identical brothers. We're doing the DNA sequencing now, and we'll get our results out soon. As Scott just came back, he's a little sore. He's walking a little slow, but he's all right. It's a long time to be in space. Jeff Williams is on our current crew of 6 up on ISS. Jeff Williams will break all of Scott's records because this is his 3rd space station mission. Each increment is 6 months. So Jeff's been up there, this is his 3rd mission, so 6 months, 6 months, and 6 months. So Jeff's getting ready to break and be the, for the NASA astronauts, the longest person in space. There's Scott with Shell Lundgren. I think Shell was just in last week here at the National Air and Space. They're eating lettuce. It's called Veggie 3. It's really important to have fresh food in space. And again, back to my journey to Mars, we need to learn how to grow and live and literally kind of live off the land. So it's a small experiment now, but we're doing looking at the bioregenerative life support systems. These are some technologies. We talked about suits in this panel, and life support systems are so critical. We really need breakthroughs in our life support systems from space station to get into deep space and deep space habitats. That's an environment that's much harsher than space station. So we're looking at all these technologies in space manufacturing. We do in space manufacturing. We have our second 3D printer up on station. So now the astronauts print their own little wrenches. And if they need a part and we didn't send it up, it takes months until we can get something else up there, so they can print their own parts if they need them. So we're really doing in space manufacturing. The SLS, the Space Launch System, big rocket that I showed you, heavy lift, we're using a lot of additive manufacturing. That's kind of the new technology that we're incorporating into our new rocket. Skip this is Scott answering a tweet from me. But International Space Station, again, phase 1 of our journey to Mars, and it's really, we're living off the Earth, but it's for the Earth. We do about 250 science experiments every increment, every 6 months. Scott did about 400 because he was up there so long. And we're looking at the technology investments as well and learning from that. So each mission is amazing. Kate Rubins goes up next in a few weeks. Kate Rubins is one of our next NASA astronauts up. She's an incredible biologist, and she will do DNA sequencing in orbit. First time in microgravity that we can do that. And let's see. I want to mention Dr. Lewis's slide ended with Elon and his dreams for spacesuits. Well, it's the new NASA, as I say. We are a funding industry like never before. It's public-private partnerships. SpaceX is taking cargo to space station right now. Also Orbital ATK right here, local company, taking cargo to our space station. So it's a new model for us. We also have SpaceX and Boeing are going to take our astronauts. That's called our Commercial Crew Program, and that's going to start, we'll be testing this year in 2017 and 2018. Then the first NASA astronauts, we have 4 already identified commercial crew. They'll be going up to space station, but not on a NASA-owned vehicle. We're paying for those services because we want to get on to lunar orbit and onward to Mars. I have the Russian Soyuz in the bottom left, the Japanese HTV. We're all in this together. International Space Station is international. 15 different countries working together 24/7 over the last 16 years. So we think it's a great model for international cooperation and space exploration. So I think of space station as the experiment unto itself for our Mars mission. We're learning a lot, science and technology. So it's phase 1, it's an experiment itself to help us over the next 2020s and 2030. I have an infographic here. It might be hard for you all to see, but it's the history of all of our probes on Mars, color-coded. For orange and red is the Soviet Union, moving into Russia. All the blue are NASA missions. There's some other colors up there too. And if you could see it, would you see, first we just tried to look at Mars, and we tried to fly by. Hey Mars, are you there? Then we tried to orbit. And it was really hard. Mars is really far away. It's really tough. It's really challenging. That's why as an aerospace engineer, I love it. Because some of our hard problems. And if you see these later ones, I don't know if I have a pointer, but 60s to 2000, we've had huge success. We meaning the world. A lot of NASA missions, everything that goes to Mars now, we help each other. The Indian Space Agency, their first attempt, MOM, they have an orbiter, and they succeeded. It's fantastic. It's a great mission. We're sharing data from our MAVEN orbiter that I told you about how Mars kind of lost its atmosphere, and MOM, the Indian observer. We're all working together, sharing data and taking data. So every day we get science coming back from Mars. Matter of fact, there's a great app. Hop on our website and the European Space Agency. If you want to know what the temperature was Mars today, I always wake up with Earth temperature and Mars temperature. It's really cold on Mars. It's always freezing, but it gets kind of close to freezing. It's like freezing and then negative 200. So download our app if you want to know what the temperature is. And then these are precursors, and what this is, all exploration, successful exploration in humanity has been when the explorers have gone to the New World, literally the Americas, and learned how to live off the land. So we get to Mars, we have to figure out, it's called in situ resource. How do we utilize what's there? It's kind of orange and red and maybe not much there. On the other hand, there's a lot of methane. we like methane. Methane will make a really good fuel or propulsion. So how can we make rocket fuel out of methane? We think about that. How it has 1% carbon dioxide atmosphere. Well, our Mars 2020 rover, our next big rover to go to Mars, it has this great experiment on it called Moxie. And Moxie is going to take that carbon dioxide atmosphere of Mars, compress it, split off those carbon atoms, and make oxygen. Not enough for a human astronaut, but it's the first time we're going to make oxygen on another planet. So again, it helps us, this all helps us to get humans there. I've mentioned the incredible international relationships we have, great framework that we already have going on in space on International Space Station. We'll be on Space Station with our partners till 2024. All of the 2020s, we have SLS going out to moon orbit and beyond. And I wouldn't be an aerospace engineer if I didn't mention the aeronautics side of the house. Very exciting. We have wonderful investments now. We're back in the XPlane. That means experimental aircraft, XPlane. There's a couple of them hanging up on the walls around here and in the whole museum. We, right now, the top one, that's a low boom supersonic transport. So we're funding, as government, we're funding the research, and we can't wait for the commercial companies to take this over. You know, I have to get to Europe on my next flight. I sure would love to go in 3 hours and not 8 hours, right? So these supersonics will fly at, you know, Mach 2, 3, 4, we'll see. So we're investing in the middle ones are ultra efficient aircraft coming to you soon. This is 50% reduction in fuel and 50% noise reduction. So these are our environmental aircraft that we're funding, looking at. They look like different shapes. And then the little one down there on the bottom, that's a hybrid electric. That's a hybrid electric aircraft that has 12 electric motors, 6 on each side of the wings. So hope to see all these flying, and I hope that we're all flying in them soon as commercial passengers. So then I want to finalize my comments and bring us back to this beautiful, beautiful view of Earth, which I call Spaceship Earth, after Buckminster Fuller. Earth is here, the sun is here. There's this really wonderful point in between. It's a gravity neutral point. It's called the Lagrangian point. We call it L1 for short. And we have our Discover mission out there. And that's a space probe. And think of it as a big space weather buoy. Instead of the oceans, you know, weather buoys in the oceans, we have this wonderful space weather buoy out there halfway between the Earth and the sun. And it's taken all the measurements from the sun radiation, solar radiation, and then it's saying, hey, Earth, here's what's coming your way. The sun is active, I'm here to tell you. So it's basically helping us. You can think about it with space weather and things like that. Plus, you can download this app, Discover, and every day you get to see beautiful images of Earth, and you see the moon orbit. And this really is the far side of the moon, not the dark side of the moon. Pink Floyd got that wrong for anyone my generation. It's the far side of the moon, and we'll go past this. Currently, at NASA, our Earth Sciences, we have over 20 satellites in orbit today. Right now, we are looking at ocean. We're looking at ocean temperature. We're looking at sea rise. We're looking at terrain. We're looking at how, you know, soil mapping. We just pointed a lot of these eyes, our Earth satellites, to Canada. In any emergency with the big fires going on in Canada, we took our satellites and our resources and pointed them so we can help with the wildfires, give information, give data as quickly as possible to help any natural disaster around the Earth. So we're very active in this sense. I wanted to show you the last century of data. Blue is good, the red and the yellow, that's a 4 degrees Fahrenheit increase. So you can raise your hand when you're born. It's the audience participation time. Thank you for playing. Now you young, there you go, you guys are young. Fantastic. Well, 2014 was our hottest year in record. 2015 was our hottest year in record. We're taking 2016 data right now, and April just broke all records. Okay, so I want to end my comments here for all of you folks in here. Spent my entire career dedicated to STEAM education. I always put in the arts because I need every single one of you out there, girls and boys. I work at Spacesuits as well, and we need the storytellers. I need the artists. You have to, you're the visionaries. You're the storytellers. You tell us what our journey to Mars looks like. You tell humanity what we're all about. Recently, I've started putting on the D. I'm pretty steamed that we're not making progress more quickly, faster, it's urgent. We need every single young person here. We need all their parents and the public as well. I think there's a really interesting axis of design and engineering. I'm an engineer myself. This is what a rocket scientist looks like. But if you don't want to be a rocket scientist, that's okay. If you're a 3D maker, I need you. You know, if you're a little designer, I need you. If you're in the arts, if you think, you know, you envision yourself as a scientist, we're just here to say, you know, we're all in. We need all the resources we can. You know, whatever your passion is, then that's kind of how I look at it. And thanks for your attention. I think we get to answer some questions.
Absolutely.
Hopefully I'm on time.
Just
so
a reason.
to boots on Mars.
Oh,
That's
yeah,
my last
absolutely.
slide.
And that's a great segue into getting some more questions going. I want to remind everybody here, if you have a question, you can step up to the microphone for our Q&A, and we'll be taking some questions online. I wanted to actually start with the question first, which kind of hopefully draws the two of your subject matter, your presentations together, which is people come to this exhibition in particular looking for some kind of answer or thoughts about where we're going in the future. We're going to Mars. Usually, Hollywood is the one that provides us with some of those visions. So I have to ask the timely question about what Hollywood presented via The Martian. How much of that, whether it be technology or spacesuit design, really kind of gives us a sense of A, what it will be like when we get there, and B, what are we going to be using when we get there?
So how many of you saw The Martian? Okay, you can stay. If you didn't, I don't know. You better get, you know. It was great. We loved it. We consulted with, first of all, Andy Weir wrote a great book. He did his homework. It was technically, it's phenomenal. It's great. He only got about 3 things wrong. And he's phenomenal. Andy was great. Ridley Scott produced a wonderful movie, so we're really happy with it. We worked with them very closely in consulting because we love it. It's a win-win. It's great for NASA. They all have their NASA uniforms on, right? And it's good for box office, I get. But what we care about is, you know, that it's portrayed. You know, we love it when they get the physics and the technology right, which again they nailed. Spacesuits. I'll let Kathy jump in. You know, it's okay. That was kind of Hollywood. What do you think?
Well, as I've always told you, the helmets are always too big. And this is a Hollywood thing, and I understand it. They have to have the nice little nice pictures of your stars, but the helmets are always big. A spacesuit helmet is very claustrophobic, claustrophobia-inducing. They are very small. They're very tight-fitting. You don't want that extra volume. But that's
duct tape? I love duct tape. You need duct tape on every mission. But that's a gas pressurized helmet, so it has like the force of like 80 pounds, kind of wanting to blow your helmet off. So duct tape's not going to quite cut it. I mean, maybe it's a good start, but you know, there were a few things like that weren't quite foolproof.
Right. We're going to go to an ongoing question next. What will future spacesuits be able to do that previous suits couldn't? Kathy.
They will be more mobile. They will be lighter. They will probably eliminate the problem of getting dust from foreign worlds inside the spacecraft. One thing that they've been working on is designing spacesuits that will attach to a roving vehicle so the astronaut can climb in and out, tend the spacesuit, clean the spacesuit from the inside, but not bring all the dirt. I have 2 dogs. My house is filthy. If I was going to Mars, the lab wouldn't be worth anything. You don't want dust and litter on the inside.
And this is hard for your online questionnaire. You'd love to do this on Mars because I got to get down and look for the evidence of past life. You can't do that in a spacesuit right now. You'd love to do some push-ups, things like that. So that's again just a sample. We can't do any of that in current spacesuits. So it has to be something that's very mobile, very light. Kathy mentioned, and it's about the people in the suits, their rovers, their robotics. We're a big team of explorers when we go searching around, and we're mapping Mars now, but we'll map all of our 50 years of exploration on Mars to date. As soon as we get people there, just in a few days, we'll go further than we've gone in 5 decades.
Kathy mentioned the vehicles where you can get into the suit without bringing the suit into the vehicle. We have an example just over here behind the audience, so be sure to take a look at that before you leave. And we have an audience question.
Hello, my name is Patrick Hutchings from Salt Lake City. And we often hear about a lot of the technologies that cross over from the space industry to our daily lives. And I'm curious, in particular, if there's any that have crossed over from the research and design of spacesuits, and if there's anything recently that we might expect to see in the general public in the near future?
Yeah, so at the high level, so we have 1,600 Spinoff Technologies each year at NASA. I'd love to share them. If you're an entrepreneur, you're out there. A couple of my favorites, they're not spacesuit specific, but portable ultrasound. A lot of biomedical instrumentation, lighter, mobile, because that's the only things we can use in our environments. So really important, a kind of handheld ultrasonics, other things for cardiovascular and catheters. So the biomedical list is long. So not Tang and not Velcro. People usually get those wrong. That's not come from NASA.
It's right here.
Exactly. And we just really cool thing is we just let out 56 patents, NASA patents. They're online. They're available. If there's an entrepreneur out there who wants to jump online, get that IP patents. We want folks to commercialize them, start businesses. They tend to be in material science, some of them like structural mechanics, planes and spacecraft, things like that. Other spacesuit spinoffs, there's been some, especially like Kathy, she's the expert. The luminized mylar, your warm blankets that you use for like marathon runners or on the beach, that directly comes out of the space program, spacesuits.
And a lot of the times you have the technology that may not have been developed for the space program, but was refined and improved. I'm thinking of all how many people are wearing trackers for their steps on their arms. And that was a technology that existed before, but and because of NASA's interest in using activity loggers on the astronauts, that technology developed and is now in all of your hands. It would not have been had NASA not taken an interest. It would have been set back and just used for military purposes, which is how it originated. You look at those technology, heart rate monitors, methods of making things, the hydroformed Lexon bubbles on spacesuit helmets. That was a technology that was developed around the time and refined and perfected for the Apollo spacesuits. It's still used today. It's the forming basis for much of the Lexan when you see on televisions and appliances, and that's how it starts. So NASA not only initiates the development, but also accelerates the development. And if you want to have an idea, I'm talking about patents, if you go to the Patent and Trademark Office website, just type in NASA on a search, and you'll get thousands. I don't know if they're millions, but I'm sure there are thousands, tens of thousands of patents. And everything that NASA does is immediately patented. So it's a wonderful tool as an historian, because I can see the step-by-step and the refinement, and one patent comes through, and a couple years later, there's something that's tacked on to the next new patent to make the technology even better.
Next audience question.
My name is Alex, and I'm from Philadelphia, and Patrick actually kind of stole my question, so I kind of have the reverse one. Now, are there any commercial technologies that you think should be integrated in future spacesuits that aren't currently?
Yeah, absolutely. Advanced active materials is one that I think we're almost there. Some people know these as artificial muscle wires, things like that. So really taking a look at materials develops and things like that. I definitely think we can incorporate those into future suits.
Well, one thing that they might develop or integrate, going back to gloves, are the metal fibers in the fingertips. So the astronauts can operate touch screens while they're in their spacesuits. That's something that I think I'll patent that idea.
And the helmet, the helmet is just, the future helmet should be, I agree with Kathy, kind of form-fitting, and it's all about the information system in the helmet. We have a HoloLens up on space station with our astronauts today, so it's not virtual reality, it's really augmented reality, because you can see out, but if you want that overlay, and that's going to be really important for future spacesuits as well. So it's a helmet, it looks like a helmet, but I can call up, what's the three-dimensional topography of Mars? Can I walk down this slope or not? Guess what, my Martian rover is a little slow today, maybe it broke. So we can just bring up a 3D CAD model, here, and say, look, fuse is out, things like that. So we're really using these tools now, so I think it'll be a really, really rich information system in the helmet, an open architecture type of IT system for future suits.
We have an online question next. How have astronauts contributed to the design of spacesuits? We've had a few of them here chaired programs in the past. They've usually had something to say about suits.
Are they really opinionated? Which is good. User. So they contribute in terms of being users. It's critical, right? Anything, like Spacesuit, needs to be beta tested, needs to be out in the realistic environment. We're here, in the lab. It's 1G. So again, the lessons learned from the Apollo astronauts is critical because they used those suits on the moon and they came back and said, guys, let's work on these gloves.
They test the hell out of them, and they complain when they're uncomfortable, they don't fit right, and they take it to their limits. There are restraining wires along the crotch of Apollo suits that came about because astronauts tested them doing lunges, doing thousands and thousands of lunges until the suit failed. So they had to have some sort of restraint wire to make sure that they didn't pop at the seams in the crotch. Astronauts are essential because they're the ones whose lives depend on the suits and who have to be comfortable in order to do the work they're trying to do on whatever mission they're on.
And I should mention too, Kathy, I don't know if you brought this up, but the transition between Apollo and later programs in the personalization of the suits themselves. They're no longer designed for each individual specifically. They're a little bit more pieced together from different sizes.
They're made out of components that each astronaut, as part of the training, has to learn to fit the suit to themselves, so they can assemble a suit from parts to make a suit that is comfortable, is not too big and baggy, because you don't want that extra room. It's not something you want a lot of size and room to move in. So the astronaut has to learn how to fit the suit, as opposed to having the suit fit it for him or herself.
For that one, I think we'll go back to the future and have custom suits for Mars.
Sure. One last audience question.
Hi, my name is Zach. I'm from Vienna, Virginia. So you guys had touched on it earlier with regards to things like touch screens and the HoloLens that they deal with things like at JPL. Technology advances so quickly. Where do you guys, in some instances, decide whether that technology is worth trying to integrate, or if it's too new or too, there's too many things to try and figure out to consider working with
great
it
question.
in the system?
Well, hopefully nothing's too new, but it has to be reliable, so we have our requirements. There's again, space is a great place because the requirements are so stringent for these, extreme, the radiation environment. We have to have radiation hardened, electronics, and instruments and things like that. So we try to know what's going on, and that's great. That's great for universities and for private industry to push us, hey, NASA. So we have something called roadmaps, technology roadmaps. We have 85, of our favorite technologies that are space specific. And so we try to push that, but we listen and we bring in external comments about, tell us what's out there, and then go through, again, really a lot of requirements in terms of making, it's all about, when it comes to human spaceflight, astronauts on Mars, make it safety and things like that. So again, it's a balance, trying to incorporate the new technology, but it really has to be proven and tried, because this third phase, when we get to Mars, and in the 2030s, we are completely Earth independent. No help from Earth. Autonomous systems, are huge going forward. We have to be completely Earth independent.
Well, I want to thank all of you for joining us today. Thank our sponsors, Boeing, and of course, thank our speakers.